welcome to today's session. I'm Sito Bejane, the author of Industrial Electronics. In today's session, we'll be looking at example 1.2, Kirchhoff's law in a Weston bridge circuit. If you can look at it in your student book, you will see this circuit. So I want to take you through step by step on how to go about solving this circuit. Now, the first question says calculate the current in each branch of this circuit in figure 1.5a by making use of Kirchhoff's laws. Also, calculate the current and voltage flowing through the R5 resistor. Now, if you can take a look at this circuit, the first thing that we may need to do is to apply Kirchhoff's current law, which means that we may need to identify some missing currents as you can see them. Now, which are those missing currents? First, let us identify those currents which are provided to us. We have I1, which is provided to us at junction A and B. We have I2 at junction B and C. We have I3 at junction C and D. But we don't have any current provided to us at CE, DE, and BD. So we may need to use Kirchhoff's current law. Now, let us look at junction BD first. Which current flows towards that junction? I1. I1 flows towards that junction. I2 leaves and BD leaves, which means that junction BD is going to be equal to I1 minus I2. Let us move to junction CE. If you look at junction CE, I2 is supplying towards that junction. I3 leaves and CE leaves. This means that the current that flows there will be I2 minus I3. Lastly, let us look at junction DE. Junction DE, we need to look at what happens at this particular junction D. If you look at that junction clearly, you can see that BD and CD are all moving towards that particular junction, leaving that junction towards the 50 ohm resistor. What is BD? BD is I1 minus I2. What is CD? That is I3. So if both of these currents are moving towards that junction, what is happening? We're adding. Therefore, junction DE will be equal to BD plus CD. BD is given as 1 minus I2. CD is given as I3. These are the currents which are present in all of these junctions. So now we can commence with calculating by making use of Kirchhoff's law, the current that is there in each branch of the circuit. First, we must take loops. So we're going to say loop 1. Take note, students, it doesn't matter how you take your loops in this circuit or in any circuit provided whatsoever. What's important is for you to understand that what is a loop. If we may look at a journey that starts at point A, going around a certain town and coming back to the very same point which you started, we call that a loop. So in this case, we are going to take the loops as prescribed in the book. But try taking different loops so that you see if you can't arrive at the same answer. Now, we're going to start off with taking loop A, B, C, D, E, F, A. That in your student book should be figure 1.5c. Now, if we look at this now, we are going to follow our loops. If I'm moving from point A to point B, I have current I1. But do I have a resistor here? No. That means the volt drop around this junction is 0. From B to C, do I have a resistor? Yes, and there's also a current. There is an existing voltage drop here. CD, do I have a resistor? Yes, and also current is here. Then there is an existing volt drop here. DE, do I have a resistor as well? Of course, and there is current also involved here. That means we are going to have volt drop here. But if you can look at EF and FA, we don't have resistors. So that means that the only voltage that will exist here will be the total voltage supplied by this circuit. Let us put that in writing. The first thing that we'll do, we'll write it as ET is equal to. We said that AB there's nothing, therefore we don't even waste our time writing a zero. We'll just move along. BC, we do have a resistor as well as current. The current is I2 and the resistor is R1. Now, if you can look at this volt drop, is considered to be positive. Why? Because I'm moving in the direction of current. The current is moving from point B to point C. My loop is also moving from point B to point C. However, if I was moving in an opposite direction, for instance, C to B, while current is moving from B to C, then the volt drop should be negative. CD, we do have a resistor still, and we have a current I3. There, I've also noted that the volt drop will be positive because the loop is also moving in the same direction as the current. I3, R5. DE, I also have a resistor still with a current. Remember, we did find that current right here. So we're going to write this as R3 into I1 minus I2 plus I3. From there on, we don't have any other resistors. Let us now substitute the values. The value of our ET is 30. We don't have the value of I or I2, but we do have the value of R1, which is 40. We're going to put it as I2. We don't have the value of I3, but we do have the value of R5, which is 50. In this case, we are supposed to multiply in like that. So I'm going to just write it as 50 I1, 50 I2, 50 I3. If you do that mathematically, it will prove that our step is very correct. We're going to retain our 30 volts, and then we're going to start working on some common factors here. We have only one I1 in this session, so we're going to put 50 I1 there at the front so that the numbers will move in an orderly fashion. We have 40 I2, we have minus 50 I2. Folks, this is what's important when you're doing your calculations, your calculator. So when you say 40 minus 50, what do you get? Negative 10 I2. You have 50 I3 plus 50 I3. What do you get? 100 I3. So we're going to name this our equation 1. We'll go ahead once again and take another loop, a second loop. Now, we're going to name that loop 2. And our loop 2 will be given as A, B, D, C, E, F, A. Remember, we said the loops that we're taking should correspond with what you see in your student book. However, you are allowed to take any loop that you may wish to desire. If calculated correctly and the rules of Kirchhoff are followed accordingly, you will realize that you arrive at the same answer. We're going to take loop A, B, D, C, E, F, A. In your student book, that will be figure 1.5D. We're still going to retain our ET this side. It's going to be equal to AB, we don't have anything. BD, we do have something. We have 20, which is R2. The current there across BD, it's going to be R2 into I1 minus I2. DC now, if you can look at DC now, our movement is in opposition of the current flow. The direction of current is CD, but our loop instructs us to move at an opposite direction. Therefore, we're going to regard that as negative. R5, I3. CE, we do have our resistors there and we are moving in the correct direction. Now, if we can look at CE, this is going to be R4 into I2 minus I3. We have 30 as the supply R2 is given as 20, so we're going to say 20I1, 20I2. We're going to say minus 50I3, and we're going to say plus 40I2 minus 40I3. How many I1s do we have here? 1. So we're going to have 20I1. We have minus 20I2 plus 40I2. This would give us 20I2. We have minus 50I3 minus 40I3. This will give us minus 90I3. Take that as equation number 2. I hope you're following, folks, because this will build up to something that will be amazing, and it will also assist you during the examination. Now, the trick part here about the third equation is that you must only remain with 2 variables. When I speak of variables, in this case, I'm talking about I1, I2, I3. If you can look at equation 1, you have I1, I2, and I3. Equation 2, you have I1, I2, and I3. But the third equation, you must only remain with 2 variables. It can either be I1, I2, or I1, I3, or I2, I3. This will assist us, and we're going to use it as a hint to continue with our calculations. Some of you may choose to make that equation to be the first one, the second, or the third. What's important is you applying the rules of Kirchhoff's correctly. Then everything will be fine. We're going to move to loop 3. Now, in my circuit here, I have noted that in loop 3, if I can take the loop as A, B, C, E, F, A, I will have my 2 variables, A, B, C, E, F, A. Let us see if it's possible. We have ET is equal to point AB, there's nothing there, but BC we do have with R1, I2. CE we do have, we have R4 into I2 minus I3. Let us substitute in our values. We have 30 volts. R1 is given as 40. R4 is given also as 40. I2, 40. I3, pardon me. Now let us look at this. We have 30, 40, 40. That will be 80 I2 minus 40 I3. We take that as our third equation. Now, I want us to continue with our calculations, but we are going to just neglect our circuit for now so that we focus only on the loops that we have here. Now, we need to start calculating, colleagues. What do we do here? The third equation should direct us on what is it that we must do, or which variable should be eliminated. We're going to use the elimination method. Now, equation 3 only has I2 and I3. This says to you from equation 1 and equation 2, eliminate I1 so that you are left with I2 and I3. Now, we are going to say equation 1 multiplied by 20. Where is this 20 coming from? The 20 is the coefficient of I1 from equation 2. You multiply the whole equation using that. Remember, always important. Ensure that you punch your calculator correctly. When you enter the exam room, start with the operation shift 9, 3 equal to AC. This will reset your calculator so that it leaves all the previous settings. Then you will get correct answers. Now here we have 20 times 30. We get 600. Right? We have 20 times 50. We get 1000. 1000 I1. We have 20 times negative 10. get negative 200. You have 20 times 100, you get 2000. We're going to name this our equation 4. And then we're going to say equation 2 multiplied by 50. Where is 50 coming from? 50 is the coefficient of I1 from equation 1. We take that, we multiply the next equation with everything. So here we are going to say 50 times 30. This will give us 1,500. We are going to say 50 times 20. We are going to get 1,000. 50 times 20, that is another 1,000. And then 50 times 90. 50 times negative 90. We are going to get 4,500 minus 4,500, I3. This is our equation 5. And then we're going to say equation 5 minus equation 4. Punch in your calculator. 1,500 minus 600. This should give us 900. 1,000 minus 1,000 should cancel out. 1,000 minus negative 2,000. 200, pardon me. This should give us 1,200. Sorry, let me use the black one. 1,200 I2. Minus 4,500 minus 2,000. This should give us 6,500 minus 6,500 I3. This will be our equation 6. Now, if you can look in your student book, you will see the same thing. It should correlate. Now that we have equation 6 only containing I2 and I3, and you have equation 3 that also contains I2 and I3, you may now freely choose which one you need to eliminate first. For this case, we are going to choose to eliminate I2. So this means that I will say equation 3 multiplied by 1,200. Where is this 1,200 coming from? 1,200, it's the coefficient of I2 from equation 6. So I'm going to multiply everything here by the 1,200. 1,200 times 30, this is going to give me 36,000. 1,200 multiplied by 80. This should give me 96,000. I2. 1,200 multiplied by negative 40. This should give me negative 48,000. Equation 3. We want to write this as equation number 7. And then we go to equation 6. We want to multiply equation 6 by the coefficient of I1 from equation 3. So we're going to say 80 multiplied by 900. This should give us 72,000. We're going to say 1,200 or 80 multiplied by 1,200. This should give us 96,000. And then lastly, we want to say 80 multiplied by negative 6,500 or 6,500. This should give us 520,000. This is negative 520,000 I3. This is our equation 8. Then we want to say equation 8 minus equation 7. So we're going to say 72,000 minus 36,000. This would give us 36,000. This and that will then subtract each other. We're going to say negative 520,000 minus 48 minus, it's minus negative 48,000. It's very important to be mindful of your signs. That'll be 472,000. I3 negative 472,000. Right? We're going to divide both sides by negative 472,000. Negative 472,000. This and that will remove each other. Then what will be the value of our I3? The value of our I3 is going to be 36,000 divided by negative 472,000. This would give us negative 0.076 amps. Remember, you have studied that if you get a negative value, it means that the current is actually moving in the opposite direction than that assumed direction. So every current direction in this circuit will be assumed until proven otherwise. Now we're going to substitute our I3 into any equation between 3 and 6. I'm going to choose equation 3 because it has lesser numbers. It's easier to work with. F30 is equal to 80 I2 minus 40 into negative 0.076. What is negative 40 multiplied by negative 0.076? This should give us 3.04. Take this to the other side. 30 minus 3.04 is equal to 80 I2. This will give us 26 divided by 80, both sides, divided by 80, both sides. Your I2 will be given as 0.337 amps. What you'll do now, you'll substitute I2 and I3 into equation 2. Equation 2 is given as 30 is equal to 20 I1 plus 20 into 0.337, forgive my handwriting, minus 90 into negative 0.076. And that will give you 30, 20 I1 plus 13.58. You take that to the other side. 30 minus 13.58 is equal to 20 I1. You divide by 20 both sides. You divide by 20 both sides. Your I1 should be given as 0.821 amps. But because the question says calculate the current in each branch, it means that we're not done here. We're going to calculate the branch. We're going to calculate branches BD. Remember, branch BD, we said it's I1 minus I2. So this is going to be 0.821 minus 0.337. 0.821 minus 0.337. This should give us 0.484 amps. We're going to calculate the current through junction CE. The current through junction CE, it's given as I2 minus I3. I2 minus I3, this will be 0.337 minus negative 0.076. This should give us 0.413 amps. Lastly, we're going to look at junction DE, which is I1 minus I2 plus I3. I1 minus I2 plus I3, this is 0.821 minus 0.337 minus, it should be plus negative 0.076, and this will give us 0.408 amps. That's it for today, folks. You can continue calculating the volt drops across the R5 resistor as well as the power by making use of simple Ohm's law's theorem. But I think we managed now to unpack some of the most difficult challenges that you might face when attempting this circuit. That's it for me today. Let's meet again.